Thank you everyone for being here so early in the afternoon. So we will try to present the results of our CEMRACS project, which is about electroporation. Before I forget, after the talk, I would like to thank all the organizers and all our team leaders. And yes, thank you for the great CEMRACS, for the great food, the alcohol, and now we will have to take care of our livers. So let's talk a bit about liver cancer. Sorry. So let's go. So we will talk about electroporation, which is a kind of new technique to cure cancer or to treat cancer. So let's go. We will start by just introducing electroporation, see what it is, and see why we care about it at CEMRACS. Then we will introduce some mathematical models. We have many different ones, so I will try not to drown you in them, but you'll have to bear with me. Then we will have to do a lot of parameter estimation, so that's actually the goal of the project. So we'll talk about parameter estimation methods, and then we will go to numerical results, because this is what we are interested in, as you can see. So yeah, let's go. Electroporation. What is electroporation? Electroporation is a phenomenon which occurs on the membranes of cells when they are subject to a relatively strong electric field. So maybe it's hard to see, but so here you have a cell, and when you have this electric field, you have some small holes which appear on the cell, which are called pores, and these are due to electrical imbalances in the cell. There can be more or less of them depending on the strength of the field, and they can also stay for a relatively short time, in which case we talk about reversible electroporation, or if the field is strong enough or lasts for a long time, then they will remain, and we talk about irreversible electroporation. So what are the applications? For reversible electroporation, in biology, it's interesting to insert new strands of DNA in the cell to modify it, or maybe to play with the cells. I hear biologists like to do this, or maybe to kind of force feed the cell with drugs that will not go inside otherwise, and to maybe cure some classes of illnesses. It's also used in the agro industry to sterilize things, I guess by just killing bacteria, and also cutting French fries. What we are interested in, however, is irreversible electroporation in the context of medicine, where it's we talk about the nanoknife, where basically we use irreversible electroporation to kill tumoral cells. Okay, so what happens in the hospital? So sorry if you just came out of lunch. So first, the patient is diagnosed with cancer, and we decide to use this technique. So we perform some pre-operational MRI. Then the day of the operation, we insert some needles in the body. This is done under imaging supervision, and when we are more or less sure that the electrodes are the good location, we apply high voltage pulses. So these are very short pulses because we don't want to have a pulse during the heartbeat of the guy on the table, otherwise it would be very effective treatment. And then after a few days, we can perform a new MRI to assess the treatment itself, and this is where we will be able to know which part of the body has been really treated, and we will know at this point whether we need to perform maybe a new electroporation procedure. So the issues with this thing are several. We would like to know better where to place the electrodes to make it to work better. We don't really, maybe we want to know which voltages, which duration we can use. But the main point is actually knowing, actually knowing where we have been treating without waiting for days. Because ideally, you would like to say, okay, I've done my treatment. Is it okay? Is it enough? Or do I need to treat more? Do I have some cancer cells left? Okay, so this is the idea of the project. So how can we do this? Oops. Okay, so previously, I had a slide about the effects on the local effects on the membrane, which was quite important. But yeah, so basically, when you have electroporation, you have holes which appear on the membrane, and this actually increases the electrical conductivity of the membrane. This is a phenomenon which is quite fast. It's the order of microseconds under the clinical conditions. Basically, so it's 1 nanosecond, and one pulse would be 100 microseconds, not nanoseconds, microseconds. One pulse is 100 microseconds. The electroporation phenomena occurs in 1 microsecond. And then after this, the membrane will start to degrade somehow, and this is a slower process, and it will also increase the conductivity a bit. So this is for us very, very good news, because it means that we can somehow detect electroporation by looking at the conductivity of the tissue. So the goal of the goal of our project is to only using the intensity we measure going through the electrodes, because this is very easy to do and it's instantaneous. And looking also at the voltage which we apply, this is what we control. Can we predict the treated area? So for this we have all this battery of models which I will just present now, and another battery of estimation methods. So our goal is to compare the estimation methods, maybe recover some realistic parameters values for these models. Some of them are very new, so there are still a lot of experiments to be done, and maybe help validate those models. Maybe we can do this. Sorry. Hopefully we can go to the end. Okay, so Very roughly, what do our model look like? So it's basically all of them sort of electrostatic sort of models. So our domain is something like this. We have the body, which has a boundary if you haven't eaten too much, and some electrodes. The very standard thing you can do is to look at the electrostatic equation, where V is the electrical potential and sigma is the conductivity of the medium. And well, you have this very classical equation with homogeneous Neumann boundary conditions on the blue boundary, which means that you have no flux outside of the body, which is realistic, and then you apply the voltage on the electrodes. Okay, so this is the general setting of everything. So let's look at this. I mean. Hmm?
You can go to overlay. Okay.
Maybe let's. No. Okay. Okay, third try. Okay, so the first model, which is very new. Okay, so this model is half phenomenological, half physiological somehow. So the idea is to look at what happens at the level of the cell and model the cell and its surrounding as a simple electric circuit. So this is the cell. And this is the inside of the cell, and this is the cell membrane. So basically, the cell membrane, inside of the cell, and the extracellular medium have they all have a given resistance, and we also modeled the membrane as with a given capacitance. So this corresponds to the fact that charges can accumulate on the membrane. Then we can write the continuity equation, which corresponds to this circuit. And if we assume that the derivative of IE is small, or we can neglect it, then we can write this evolution equation for the current I cell. And then we can close the system using the other equations. And the idea is to use this to write an equivalent equation at the continuous level. So this is what we can do. And this is what we obtain. So this is our first model, which is the static B-phase model. Okay, so here phi E is the electric potential outside of the cell. JC is the electric field inside of the cell, and EM is basically the difference of the two, and is the transmembrane electric field. So sigma, all the sigmas in this talk are conductivities. Sigma E is the outside, sigma C is inside, and sigma M is the conductivity on the membrane. and it will depend non-linearly on the intensity of the electric field, and it will the dependency will be very simple. It will be a base conductivity for low electric field, so without electroporation, and then when the electric field is high, then this will increase to the electroporated conductivity. So basically we will take sigma m as a sigmoid. Okay, so starting from this model, we can write everything in terms of Em and phi E, and this is we can rewrite the model like this, and we get a kind of it's a nonlinear Laplace equation, I would like to say, where this, if sigma m is a sigmoid, this is also a sigmoid. So we get, in the end, we get an equation like this with the boundary conditions which are, I talked about before. So this is the first model we worked on, which we call the standard model. Here, maybe somehow the nonlinearity here is meaner because it hits directly on the high order terms, whereas previously it was not the case. Okay, so now we have another model, which is the B-domain model. So this one is a bit more, it's derived in a, I would say, more rigorous way, because we look at we write basically the continuity equation at the level of the cell. So we have no divergence-free electric fields outside of the cell, inside of the cell, and then we have some continuity conditions on the membrane. So this basically means that the current flux on the membrane is the same from the inside and from the outside. And then this is basically the same condition, but on the membrane itself. So this is kind of a gradient, but since the membrane is infinitely thin, it's just a difference. Okay, so starting from this, you can do an homogenization limit, and you end up with this model, which is very similar, and which we call the static B-domain model. So this limit is rigorous in the case where the dependency of sigma m here is on this difference. So this limit has been done in the context of electrophysiology, where the dynamics are much slower, so we don't look for the same effects. And if we try to apply this model for electroporation, it does not work. In particular, if you have 2 electrodes, you will not have electroporation at the center, which is not good. So what we can do is try to do a small phenomenological modification and take a dependency on the gradient of UE, which is the potential outside of the cell. So this is nice because it matches experiments qualitatively, but it's, then this derivation is still work in progress. Still work to do. A word about the boundary conditions. We still have no flux boundary conditions, and non-homogeneous Dirichlet boundary conditions are imposed on UE. Basically, the idea is that when you stick the electrode in the body, then you will destroy any cell, and then you will consider being only in extracellular medium. Okay, I think now we can talk about dynamical versions of these models. I think there's not too much to say, but basically here the idea is not to forget about the capacitive effect of the membrane and to keep this time dependency term. Otherwise, it's the same equation, and the same for the B-domain model. This is interesting. Classically, what has been done in electroporation is only considering static models because they are simpler and we have much less parameters. But now we have access to complete chronograms of the intensity. So we have much more chances of capturing the fine dynamics and of the electroporation by using these models. Yeah. Okay, so when we also one thing when we use dynamical versions, we can have dependency. I mean, it's interesting because we can have a time dependency of sigma m, which is done in for now in a phenomenological way. Basically, we write equations for the phenomenon I described at the beginning. You have the base conductivity, and then you will have increase in conductivity, which is due to the electroporation, which is very fast, and then you will have an increase in conductivity, which is due to the permeabilization of the membrane. So this degradation of lipids. Yeah, I mean, yeah, we can write equations for this. I mean, the exact form is not that important. Here we have you have an idea of how the field evolves with time. So here's the outside electric field. You can see that it reaches equilibrium very fast. So here, this is 1 microsecond. This is 5 microseconds. This is 20, and this is 100. So in 5 microseconds, you are basically at equilibrium here. Basically at equilibrium here, this is x1, which corresponds to the fast dynamics. This is the slower dynamics, and this is the transmembrane potential, which also evolves slowly. Okay, so just to sum up, all the parameters we have in our model, yeah, it's a lot. So we don't want to estimate them by hand. The data we have, for now we have clinical data for 3 different electrode sizes. Voltage we can have basically a lot, but the data we have 5, and then for the dynamical models we have around 20 samples in time. Okay, so this is it for the modeling part. Now we'll have to do something about these parameters and try to determine them from the data we have. Okay, so let's formalize a bit the inverse problem. We have our parameters will be symbolized with theta here, which is in parameter space with a given norm. Y is the solution of our problem. So here it will be the solution of the PD problem. And we have operator L, which maps the parameters to the solution, assuming that it's unique and well posed, etc. We have the space of observations, so things we can measure. So in our case, it's the intensities. And yeah, we can map the solution space to the observation space using measurements, which with the measurement operator C. Okay, and so the goal is to invert this map, so if we call psi the map from parameters to observations, we want to invert this map. We want to go from observations to parameters. And this is done by minimizing, I mean, at least formally minimizing this this functional where delta diamond is the a priori estimate you have on parameters. P diamond is somehow the uncertainty we have on these parameters. And so this is the error, how much we drift from our prior estimate, and this is the error we do in the measurements. With this norm, it depends on R, which is basically the measurement noise. When you do a measure, it's never completely accurate. Okay, so I think now we can have several measurements. So we just sum here. Basically, an overview of the methods we have. You can do gradient descent. In our case, it's very hard to do because you need to compute the Jacobian of the dysfunctional, which depends on the solution of a nonlinear PD, very nonlinear in some cases, so we don't want to do this. It also requires some tuning, line search, etc. We don't want to do this, so we will focus on these two. The Monte Carlo method, which Thuy will present, and filtering methods, which I will talk about afterwards.
Okay, thank you, Gaspar. Now, we talk about the Monte Carlo methods. At first, we say a little bit about the computing experiment. Computing experiment, what is this? It actually applies the computer to solve a problem by performing computational, which is based on the mathematical or physical model, using the quantitative computation and relative parameter. And these areas conclude computational physics, computational chemistry, and computational biology. Monte Carlo methods is one of the most popular computing experiment methods. And what is the Monte Carlo method? It is wide. It is wide computational algorithms that use the random samples to obtain the numerical result. And in fact, there is a lot of complex mathematical or physical models, physical problems that is difficult or impossible to solve. And in this case, Monte Carlo method is often used, and it is useful. And to understand the Monte Carlo methods more, we will see how does this work. So the Monte Carlo methods attempt to model the problems by directly simulating simulating the necessary theories from the requirements of system, such as the interaction between the objects with the other objects, or the objects with an environment. And so we have an input population, and we just take randomly the sample from the input population, and each sample have to mimic the characteristics from input population. If you know the distributions of input population, and each sample should follow the given distribution. If we don't have too much information about input population, and we just take randomly samples with the sentence distribution, and then we compute the synthetic data over and over each time using the different sample. And link to the standard static model. And the input population here is the parameter theta containing the 4 parameters that Gaspar already mentioned in the previous slide. E threshold, gap, sigma zeros, and sigma 1. We don't know real parameter theta, and we have to estimate theta. We just know observed data, that is the observed intensity, that we take some data from the hospital. And when we get the synthetic data, and we just have the comprehensive view of the possible outputs from our input, and and the solutions of the problems. That means the estimated parameters is the samples in order that the residuals between the synthetic data and observed that test is closed. Applying the Monte Carlo methods to the standard static models, and we have 3 steps. The first step, because we don't know, we don't have too much the information theta. We just know the 4 parameters is threshold, cap, sigma zeros, and sigma ones is positive, and that's all. So we suggest the priori values of the priori parameters value theta 0, and the values of theta 0 I take from the literatures of the articles of Olivier Zulicano, and so like some heavy problems, and maybe you can see the values of theta 0. Don't worry, when we go to the slides of the results, and we can see something. And the second step, we compute the corresponding the intensity with the 3 different electrodes diameter and 2 different voltage. And the last step, we use the least square error minimization to find the best matching set of the parameter. We talk about a little bit least square error. So the observed data is Z, and bit size of theta I is the corresponding model estimates, and we compute the residuals between them. We are not sure the residual between them is positive or not, so the better way is to take the sums of the square residuals. That means the sums of square residuals is only zeros if every residual is 0, and it's better. And estimated parameters is taken as the theta star is argument of the z theta I. So from the priori value theta zeros, that is containing the 4 parameters, and you can see the values in the first table. And we generate the set of parameters from priori parameters of the form uniform distributions with some variance, and we performed with the different size of the parameter set, and you can see more parameters. You can see more bigger size of parameter set is, and more, and the better of the minimum of square residuals we get. And so next we will talk about the Kalman filter methods, and Gaspar will talk about it.
Thank you. So yeah, before I go on, I would like to say that the results that we presented are based on actual. I mean, it's based on real data, and it's the only ones we have on real data. So I think it's great that you did this work. Otherwise, we would have only synthetic data, which is a bit boring. So to finish, I would like to present what we did with the Kalman filtering. So yeah, I have to do this slide somehow. So very quickly, Kalman filter on the linear case. So what we want to do is to estimate a given state, which is the true state, and we know by x. and it's if you have a time discrete evolution, then the evolution is given by this operator L, which is linear plus some noise. The noise is not noise on the measurement, it's noise, it's basically it models the dynamics of the system that you don't know. L, however, you know. And the point is how should we model this? This is how it behaves in reality, but we cannot observe xk directly. We will use a model which is x hat, which will evolve like L without noise, and we will be able. The only way we will be able to compare these two is through observations. It's in another space. So basically, if for example, you would have velocity and speed. Maybe in the observation space, you can only observe velocity, only position. Sorry, if you have position and velocity, you can only observe position. For example, for the GPS. Okay. So starting from an estimated space, estimated state x k hat, and an estimated uncertainty. Which is the covariance essentially between the true state and your estimated state. You can predict the new position by applying L, and the new covariance by applying L on both sides, and adding Q with Q is this noise, the covariance matrix associated to this noise, and then you will update your prior estimate. By looking at the data, so zk is the observation you did plus some noise. This is the observation operator that is the same as the slides before. Here is here you will add the noise. This is the gain, and then you will basically update the new. So this should be capital X. You will update the new estimated state and the new covariance. So this you can do because it's all linear. So all of this is very natural if you look at it for a moment. The problem is that linear is not always. We don't have all linear things. So. How can we use this for parameter estimation? So basically, you have your state. You can plug the parameters inside your state, have no evolution laws for the parameters, and just let it run. The problem is that if your state space is very big, like for us, it's the PD finite element thing. Finite element space is very large, so you have to deal with matrices which are much too big. And this works for linear operators. And also, linear evolution operator and linear observation operators. So in our case, we have a space which is too big, operators which are not linear, but this one is linear, so at least we have something. To do this, we have extensions of the linear Kalman filters. So this is to deal with the nonlinear part, and to deal with the huge state space we have reduced order Kalman filter, which I will not talk about. But this is what we used. A very quick review of the numerical work we did. So we worked with all of our code is written in Python. We worked with NumPy, like everyone working with Python do. Phoenix, which is a nice finite element library, which I recommend. And FilterPy for Kalman related things. We didn't use FilterPy for the Kalman filter itself. We wrote it ourselves, but there are some small things that we used, like initialization and so on. So what we did, solvers for all the direct problems, which I did. In the static case, the dynamic problem, it's still we have some tuning to do. We have a Monte Carlo estimator, which Tui worked on. We wrote a general Kalman filter. The library is maybe a very big word here. but this is what we used for static parameter estimation. And once we have, we will have our dynamic solvers, we will be able to use this for dynamic parameter estimation. And then we have some glue code to do the estimation itself. This is essentially the work of Cécile. Okay, so now pictures. This is just very quickly the kind of results you can get, because I've shown you only equations for now, so it's time to see what the solution look like. So in all of these things, we only work on the upper right quadrant because of the symmetries. So you can basically, you should extend this picture to all of it by symmetry like this and anti-symmetry like this. Yeah, like anti-symmetry like this for the potential. Sigma is symmetry. So sigma is the conductivity. So you see that you have a nice electroporated area, which will go like this around the electrodes. It's nice and precise. Here is what the electric potential looks like. It's what it is. And here is the norm of the electric field, which you can check that the contour lines here matches the contour lines here, which is expected. So this is the static standard problem. The most simpler, but also maybe the most complicated to solve numerically because of the non-linearity. This is what the B domain looks like. So we cannot really compare the pictures for sigma directly because we have different set of parameters, and these are the parameters for these pictures here are chosen a bit arbitrarily. Okay, so but we have the same kind of pictures, and for the dynamic, so this is the dynamic B-phase model. Yeah, maybe we can just. So this is at 1 microsecond. For you can here you have the voltage and here the measured intensity. So we are still in the front. You see that this is 0.6. So and this is the electroporated region. So it's already not saturated, but half of what it can be. And if we go on, if we go on here, it's at 0.8, so it's very, very fast. Here I have to say that we don't have the spike that I've shown you at the beginning because we still have an issue in the code, but this is to show you an idea of what the dynamic look like. And here you can see on X2 that it's very slow. We are at 0.018, so it's much, much smaller than here. Okay. So convergence curve for the Kalman filter. These are all the estimations done by estimating parameters independently. So it's on synthetic data. We choose we fix 3 parameters and estimate the other ones. We have nice convergences. It's a bit slow for the electroporation threshold. And we see that on the slope of the sigmoid, we have no sensitivity. So basically, we can forget about this parameter. This is what it means. When we estimate the electroporation threshold and the electroporated conductivity, we have also a nice convergence. And if we also add the base conductivity, we also have something. The sigma 0 is, however, much slower. Okay, so let's conclude. So we have done all this implementation work. We have some clinical data analysis thanks to TWI. We still have to work on the dynamical problems, but this is, I hope, going to happen very soon. And then we have, I mean, for me, it was very interesting. This is a lot of software, of coding, etc., but there are lots of very interesting theoretical questions coming. So, yeah, thank you for your attention.
said you have a training center. What is the time containage?
So
I can imagine it's huge. I mean, it's very small. The precision of the
yeah, it's the order of 1 microsecond. A bit under.
But the length is only 100 of microseconds.
Yeah.
So, okay.
So we capture. Maybe we don't capture the spike, but not. I see we capture it, but it's maybe one sample. But the long time dynamic we have a lot of data. The problem is that all these machines are, I mean, they still quite prehistoric in terms of technology, so there's a lot of work to be done on the machines themselves.
So it's relatively decent amount of data. So
No, yes.
Yeah. So good afternoon to everybody. As we said, we will talk about interface reconstruction for 2D compressible multi-material flows. This is a work that was supervised by Laurent Dumas, Philippe Hoche, and Thomas, who's there. And the students are me, Igor, and Theo, who you met, but it's not with us at this moment. So let's start with an overview of the contents that we will talk about today. We will start by placing the problem of interface reconstruction on why is it useful, which are the methods that are done in the literature in order to face this problem. Then we will explain which is the method that we choose to work with, the peer method, and the goals of our project. And then we will enter into details, and we will talk about what we did actually, so the reconstruction of curved interfaces for two materials. We studied the robustness of this method, and then we extended to three-material case. And then some issues that we had in the case of three materials. So first of all, what is the interface reconstruction and which is the context where we place in? So this problem appears, for example, in the case of image segmentation, or in our case, in the case of multi-material hydrodynamic simulation with ILE. Because when you're working with the arbitrary Lagrangian approach, what you do is that you see the problem in a Lagrangian perspective. So when your material is moving, also the mesh is moving with it. And what you can find is you can face some very distorted meshes that you want to remap on some more regular ones. And when you remap the meshes on regular meshes, on more regular ones, you find yourself with some cells of the mesh that are mixed. And mixed, I mean that they contain the presence of two materials. So you want to actually know where is one material and where is the other. And so there are three families of methods that try to understand what is the interface between the two materials. So a first category is the interface reconstruction method. The most famous one is Young's method. Young's method is a very robust method. And what it does is that it reconstructs one interface per cell. It has some advantages because it's able to conserve the partial volumes. With partial volumes, I mean the concentration of each material on the cell. It's robust and it's cheap. But the interface that is reconstructed with Jungs is not continuous. So you will see a picture later of what I mean with that. Then we have another family that is the family of interface tracking, in which we can find level set method. Here, the interface between the two materials is seen as a zero-level set of a particular function. Thanks to this method, we are able to construct a continuous interface, and the method is really robust. But this time, we do not ensure the conservation of partial volumes on each cell. So you see that we have some drawbacks in all the two categories, and also some advantages. Then there is also another family of methods, that is the antidiffusive method. This is quite different. And the idea is that actually when you're studying this case, your material can diffuse a lot. So you want to prevent it to control the interface. But we focused on those two and actually wanted a method that was able to combine the advantages of these two methods and to avoid the drawbacks. And so the method that we study is the peer method that was proposed in 2017. And it's able to construct an interface that is continuous. It's able to preserve the volume fraction on its cells. It's robust for the moment on Cartesian meshes. And it has a moderate computational cost. So just to give you an idea of what we'll discuss later, you see that if you want to reconstruct an interface, so here you have what you see, you have your domain with two materials, one on the exterior and one on the interior of the G shape. You see that if you reconstruct the interface with the peer method, you have a continuous interface, and the volumes inside of each cell that is mixed, where you find the two materials, is actually preserved. If you do the same with the Jungs method, here you don't see, but you have the meshes. You have one interface reconstructed by each cell. And here the volume is conserved, but it's not continuous. So you see the advantages of using the peer. So now Igor will explain to you how does it work.
So the peer methods. The peer is a contraction of dynamic programming interface reconstruction, and I will explain in a few minutes what dynamic programming actually is. The idea of the algorithm is first to extract from the mesh, the global mesh, only the cells that where the interface lives, the cells in which there is two materials, and then to apply a minimization problem on this new submesh. And after the first step, you have a non-corrected first approximation of the interface that you have to correct with an additional step of volume correction. So I think that it is not really clear. So let's draw. Suppose that you have a very coarse mesh, a Cartesian mesh first. And that your interface between, that you have two materials into this mesh, and an interface that behaves like this. Okay, blue is not a good idea, but okay. So there is an inner material into this square and an outer material outside. The algorithm gonna construct some internal and external curve with knowledge of partial volumes in each cells, because into this kind of cells, you have some partial volumes that are, those are some pure cells. Here you have something like this, but in the interface, on the cells crossed by the interface, you have some partial concentration that are, for example, given by 1/2 and 1/2. So the algorithm is going to track those cells and construct two curves, an internal and an external curve. And something that you can see is that we now identified a set of edges that are crossed by the interface. And actually, a good first approximation of the interface is piecewise linear reconstruction of interface, where we consider only the points in the edges crossed by the interface and realize them with some linear function. Okay, so in order to find this, to solve this problem, the idea of Zapier was to introduce a functional to reformulate it as a minimization problem. So this is the cost functional of Zapier, where P0, P1, etc. to Pn are the points chosen in each edges. So, for example, here we have P0, and then we want to reconstruct all the P. In order to get some continuity, we impose that P0 has to be equal to Pn. Okay, so you see here with these notations, I indexed by I is the internal point. So for P0, this is this one. And EI is this point. Okay. So in this functional, you have a first term that corresponds to the difference between the volume induced by the choosing point and the targeted volume. For example, here, if we have Pi and Pi plus 1, the volume between Pi and Pi plus 1 on the internal curve is actually this volume. And it is compared to the partial volume that you already know with volumic fractions. And there is an additional term that corresponds to penalization on the perimeter. But there is a drawback with this penalization because the lambda parameter is a parameter fixed by the user, and it has a big impact on the shape on the solution. So giving a strong lambda, we will give a strong a priori on the shape of the solution. So, okay. Now, you have your functional. You know that you want to apply a minimization problem. You have to discretize your problem. So this is done by actually only discretize all the edges that are crossed by the interface. So, actually, you split your edges in a similar way each time. And then, you want to find a shortest path, in a certain sense, that will minimize a distance given by this functional. Actually, this is the shortest path problem. That's why we can use a particular family of algorithm that is, in this case, the dynamic programming. So here there is a bit formalism, but it's not really important. The thing you have to understand is that we only are searching the shortest path, and we don't want to evaluate or to enumerate all the theoretical paths to compare them. So here we introduce a gain function that corresponds to the cost of a transition between a point to another point. For example, the gain function between the point Pi and Pi plus 1 will be the evaluation of this first functional on this cell. Okay, and S in our case is only the discretization of one edge, because we use the same discretization in each edge. Okay. So what theory about dynamic programming tells you is that you can reformulate this this expression as a set of equations, and introducing a Bellman operator, you can reformulate it again as a recurrence formula that tells you that you don't need to evaluate all the paths to obtain some information about the cost of the functional. Actually, if you want to determine the cost of the functional for the path between P0 and Pi plus 1, you only need to know what is the shortest path between Pi plus 1 on the previous point and the shortest path between Pi and P0. That's why you can drastically reduce the complexity and pass from complexity exponential in the number of cells into a complexity that is almost linear, because we fixed some small s in our cases. So I said that we need also correction phase. because at the end of the step of dynamic programming, we reconstruct some piecewise linear interfaces that don't preserve the partial volumes. And so the idea of DPR is to add in each cell a control point to increase or decrease the volume induced by the first step. For example, if here you have to add a small volume in this cell corresponding to the inner material, DPR gonna construct a point here and add the volume in the triangle induced by this new point. So here we have an illustration of DPR after his second step compared to Young's method. So Young's is still not continuous, and we try to reconstruct a circle. And here we use a discretization of edges corresponding to 50 points on each edge. So, okay.
Okay, so all of this actually was already done in the paper that we started to study. So the question is, which are the goals of our project? How to extend this work? So the first idea was that we want to pass from a polygonal reconstruction, as Igor explained, to a curve reconstruction. This can happen because maybe what you want to approximate is, for example, a circle. So you can imagine that a curve reconstruction could work better, or also because you want to work with the curve meshes. So there is an interest into improving this point. And then also, what we said, the method that was proposed works well in Cartesian meshes. So we wanted to see what happens if we pass to unstructured meshes, and how can we improve the robustness of the method in this case. And then as a third point, there is quite an open question, how to extend the method to three materials. So we will discuss it later. So the first thing, how to pass to a curve reconstruction. And the answer is to use the Bezier curve. So what happens if you consider a cell of your mesh? After the first step of the Peer method, what you find is the 2 points that in this moment I will call P0 and P2. So instead of having a polygonal, what you want is you want a curve. So Bezier curve works well in this case because they depend just on 2 parameters. They just depend on a control point that we actually already impose, that is P1. And once you have the control point, you just need to impose a weight, omega, in order to reconstruct your curve interface. So in this case, actually, what we mean is that after the first step, you had a linear interface with a partial volume that is beside the interface. Imagine that you want to, in order to achieve the attained volume in this cell, you want to increase the volume, so you add a control point. And now, the actual partial volume in the cell will be the sum of this area and of this area. So Bezier curves are nice because, first of all, we just need 2 parameters, one of them we know. And second, because to compute the area beside the curve is actually quite easy once you know the area of the triangle. So once you know the area of this triangle, you just multiply this area by a function that depends on omega. And I forgot to say that actually the weight omega for the moment is a weight that we impose before the algorithm. So it's something that is known and is constant all the mesh. So just to have an idea of what's the shape of this function is this. So this is just to remark that actually the choice of omega implies a choice of the type of curve that we use. For example, if we choose omega equal to 0, this means to consider a degenerate curve, so a straight line. If we take omega between 0 and 1 will be an elliptic curve. Omega equal to 1 will be a parabolic curve. And omega greater than 1 will be an hyperbolic curve. And also, another thing, omega can take value between 0 and plus infinity, and also plus infinity. What does it mean when omega is plus infinity? Actually, when it takes this value, we come back to the case of a linear reconstruction. So by extending the method using this kind of curve, we can actually go back to the original Depere method by taking just omega equal to infinity. So just to see a comparison between the reconstruction of a circle between Young's and polygonal Depere and the curve one, you can see actually the difference that, I mean, it's quite clear. The circle is well reconstructed. As Igor said, there is also the parameter of penalization that has to be chosen and has to be, I mean, chosen well in order to get a good image. This is a bit of drawback, but we get good shapes. And so we tested other test cases, all on structured meshes. So first of all, we did a bigger circle with a finer mesh. And here what you can see well is in this zoom of a cell, you can see well the 2 points of the interface, the control point that is added, and the curve interface that is reconstructed. Then we had fun and we tried to reconstruct a square. But, I mean, the square is not the best choice in order to use curve reconstruction, but it was just to make you see that actually it works pretty well also on straight lines. And if we randomly displace the Cartesian mesh, we still get a nice picture. In this case, maybe we could use a better an omega equal to infinity. It was just to test. And then the G case that I showed at the beginning, and also here. So what you could remark in this image is that actually you don't see a lot of curves. So you would expect to have curves here and here, but you don't see it because actually the first step of the minimization of the energy works pretty well. So it gives you a curve that is quite accurate. So the correction that you have to impose are really small, and you don't see it here because it's small, and even here. So you have to correct not a lot of cells. But this means that the method works well. So the problems arrive when we pass to unstructured meshes.
When we tried to apply this algorithm to unstructured meshes, we were confronted to a new kind of problem for the correction, because sometimes after the first step of Depere, I mean after the dynamic programming, the interface reconstructed passed through some vertex of the mesh. For example, if you have this case where you know that you have to pass through these edges, it is possible to have something like that, because the same point is chosen in this edge, and then when you want to correct the volume into this cell, you don't have the necessary hurry under this point to correct your volume. I mean, you will search a control point in order to draw new triangles under which you have a sufficient area to correct your volume. But if you have 0 here, your control point will go at infinity, and you construct something like this. That is kind of thing that we can see here. And actually, we also have some cases in which we have some points going to infinity. So we tried to deal with this problem and to treat them, to treat those singular points. So a first idea given by our supervisor was to change the discretization in edges and switch to Chebyshev node in order to avoid the passage through mesh vertices. So it gives some better results, but still not sufficient. So another technique we tried was to change the searching direction for the control points and to go in the direction of the center of the cell instead of the bisector. Because, for example, if you have a triangular mesh and an interface that is that has this kind of shape, bisector gonna search a control point in this direction, and you not always have sufficient volume to correct your targeted volume. So it seems to be better to search in this direction. But when you have too small area between your interface and the internal curve, we still have the same problem. So finally, we tried to add a new penalization term into the global cost functional. And the new penalization writes like this. And actually, this is a kind of local norm ponderated by the area between those 2 points, the interface and the internal curve. And you can see that if this volume here is too small, then this term gonna explode and the energy will be so big that in the dynamic programming, the path will never be chosen. So you can see that using this penalization, we don't have the singular points problem no more. Okay. There is still 50 points by edge on this picture. And okay. So now we can discuss the extension to 3 materials.
Okay, so as I said at the beginning, the case of 3 materials is actually quite an open question. So if you consider the family of methods that we discussed in the introduction, actually even Young's method and level set method are not quite adapted to the extension of 3 materials. Because, for example, Young's will reconstruct some interfaces that are all parallel between them, and level set method will find some quite of empty zones. So this was a challenge, and we had a lot of ideas of how to apply the peer method in this case. So let's imagine that your test case is the following. So you have your domain with 3 materials that are disposed in this way. Material 1, 2, and 3. So the first question is which material do we reconstruct as the first one? In which way? So for example, you can think about, okay, I start from this material, I construct the interface between material 1 and 2. So I reconstruct something like this. Then I reconstruct the interface between material 2 and 3, and I reconstruct something like this, and so on. But this approach has a lot of drawbacks. For example, we are not able to compute the internal and external curves as closed curves. And also, it increased a lot the complexity of the problem and the cost. So what we thought is that actually a good strategy was to apply the first step of the peer. So when I mean first step, I said the minimization step 3 times. So for each material, for example, material 1, I will reconstruct the interface between material 1 against the 2 others. So we will have an interface of this type. And it's a closed interface. Then I consider material 2, and I do the same thing. So I have an interface that is closed, and the same for material 3. In this way, actually the cost is not increased, and also all the computation can be parallelized. So you can do it in separate, in parallel. Once we have this, we have a problem, because we find ourselves with 3 sets of different interfaces points. And what we want is just one interface. So, for example, we have something like this. You can see here that instead of having one interface, here you have 2. And also, I forgot to say, the triple points are treated in a separate way. So we impose an arbitrary point here, and we glued it to the other. So here, we need a further correction step in order to get one interface, just one. So we applied the most naive idea that we had. It was just to take the averages of the 2 coordinates and glue them, and take the average in order to get just one interface. And this actually worked. So we had a further correction step of the optimal coordinates, where we average those coordinates in order to get just one interface. So at this stage, we have one interface that is continuous, that minimizes the cost functional, but it still does not preserve the volumes. Okay, so we need an additional step, a last step, in order to correct the volume in each cell. And what you can observe here is that you have 2 different type of cells. So you have cells in which there is just the interface between two materials, and cells in which we have the presence of three materials. And clearly those two cases have to be treated in separate ways. So for the case of two material cells, what we do is what we did until now. So we have our points, we have our volume here. We want to correct it, let's suppose that we want to increase it. We add the control point, we trace the polygon curve, and then we trace the curve. So this does not change with respect to the case of two materials. What changes is the three material cells. So the question about how to treat three material cells was first of all that we didn't want to give priority to a material. So let's suppose that is material 1, 2, and 3. So we didn't want to choose a material as the first and then give him priority. And so what we observe is actually that if the volume inside the cell is not already corrected, there will be always a material that behaves differently with respect to the others. So there will always be a material, for example this one, that want to increase this volume, and the other two they want to diminish, or vice versa. And so if we study this kind of vector, the vector of signs of the correction if you want, you are able to identify the material that is different from the others. And when you find this material, you will treat them as a first. Because if you do this, you can think about that this material is the one that needs the most correction. So what we do now, let's suppose that this material wants to increase this volume, and the other two, they want to diminish. So for this material, you know the 2 points of the interface. And what you do is that you compute as we did before, a new control point. No, let's do, okay. I changed my example because it's clear. Let's say he wants to diminish and they want to increase. So you add a control point and you trace this new interface, but the polygonal one. Okay? So as the first example of Igor. And this point, so now this cell has the corrected volume, and this becomes now your new tripole point. And now what you're left with are two materials that doesn't have the corrected volume, but they just share one interface. So at this point, here, you have 2 points, and you can correct the volume. For example, let's suppose that at this stage, he wants to increase and he wants to diminish. You add another control point, and here you find your final interface corrected. Okay? So in this way, all the cells are corrected, and we have our final results, where you see that you have one interface. So the two interfaces that you see here are actually the linear interface that comes from the first step, and the corrected one with the curves. And so you see here that we are able to reconstruct the circle in quite a good way. And okay, so here it looks like that is close to the interface. Well, actually it's not really close. And the fact that is going really high is due to the choice of the penalization. Because the more penalization you put, the smaller will be the perimeter. So this was quite a small penalization. So this works well, but on Cartesian meshes. So at the moment when we passed to unstructured meshes, we had some issues.
So here we have an illustration of the same algorithm, but on unstructured mesh, and it looks to quite well construct the interface. But if you zoom on the top, the thing you have is that the triple point isn't the good one, because if you look at the two top triangles, the theoretical interface behaves like this. But here, the algorithm chose to put the triple point into this cell. And this is because we have two adjacent cells that share 3 materials. And this is something we didn't plan to handle. For example, here we have an external material, on the this one is 2, so you have 2 here, and 3. So okay, but actually this is a drawback, a common drawback of all interface reconstruction algorithm, because this case can be identified by the behavior of the third materials. Actually, we have a single edge that is crossed twice by the same interface. And if we are able to solve this problem, to detect this problem and to adapt it on dynamic programming, we should be able to treat this case. So that's what we try to do. And just for the context, there is another application, because when you have some materials, when you have one material compressed between 2 others, this case can happen. For example, if you have an inner material, let's say 1, trapped into 2 others, 2 edges are gonna be crossed twice. So this is not particular of this circle. So we had many ideas in mind to treat this problem, but some of them were really too complicated to implement. So first, a naive idea was to refine locally the mesh, but we had a problem when we wanted to scatter the partial volumes on the new refined mesh. So we also imagined that we can change the topology of dynamic programming only locally in order to detect, to find 2 points at the same time when we evaluate this edge in the algorithm. But this is something that is hard to implement in a general dynamic programming algorithm, because you consider the structure as an n-dimensional array, but I don't speak. Okay, so we also plan to change the discretization on segments in order to impose a first pass through only a part of some edge. But the idea we implemented finally was a combination of mesh refinement and adaptive discretization, because we treat independently the filaments, so we can track filaments looking at the graph of our interface quite easily. So when you have your filament, suppose that it has the following shape. Our idea was to simply divide by 2 all the cells by adding some fictitious frontier, and then to force the dynamic programming to pass through these half edges. And then you can see that all edges are only crossed once. So it works pretty well. But when you do this reconstruction, you also have to link those 2 points to the global solution of the minimization problem. And this is what we have to do. Because you have a problem on this cell where the volume are not scattered. And so for the question of partial volumes, we simply divided by 2 the partial volume in each cell in order to give 1/2 in all new cells. So now we're going to conclude.
Well, just to conclude briefly, just to remember you what we did. So the first thing was that we modified the peer in order to reconstruct curve interfaces. So we added this curve. We improved the robustness of the peer in the case of unstructured meshes, just by what Igor explained. And then we found a way to extend the peer in the case of three materials for the Cartesian meshes. So we are still working on the structured one. And for the perspective,
so we have to finish the implementation of the treatment for filament issue. We also plan to adapt the weights of Bezier curve in order to not have a global omega for all our problem, and because we have a relation between angles and omega for the circle. And for the long-term perspective, we plan to test this algorithm on more complicated unstructured mesh, and to extend it to n material. Here you have an illustration of a four material case where you have an outer material and three different material in, but only with triple point, considering three different materials. Okay. So thanks for your attention.
Well, you choose it. You choose it arbitrarily at the beginning. You fix it for your algorithm, and then you can try to adapt it once you see the simulation. And for example, for the circle, for example, the circle is quite a good example because you can think to adapt, because there is actually a perfect omega for the circle case, but it requires to compute an omega for each cell. So we didn't implement it. We fixed an omega for all the domain and. Yeah, another thing that we can do, not also for omega, but when you reconstruct your circle, you can find yourself with things like this, so with little bumps. So it means that you didn't choose well your omega. But what you can do, you could, for example, add a penalization term in order to study the tangent vectors to this curve and to impose that they glue, for example. But we still have to see it. To explain that, to speak? Okay. For the control point in the algorithm, we use a dichotomy algorithm. So, because we tried the analytic way, so by imposing the actual control point that should be used, but didn't work. So what we do once we have our segment, we place ourselves in the middle of the segment, and we choose the direction of correction. So imagine that this is your volume and you want to increase it. So you choose this direction, and then you construct this curve, and with the dichotomy algorithm, you compute the real coordinate of the point, the one that satisfies the equality of the partial volumes in the cell. And this works also for the curve. You do the same. It's also always on the bisector, except for the case of unstructured meshes, where we change the direction, and instead of going to the bisector, we go to the center. Yeah, the average.
So actually, this is an arbitrary choice. You are talking about the triple point? Yes. By solving independently a dynamic programming problem on the left materials, and another dynamic problem on the right material. I mean, we applied the peer 2 times in this situation.
So here you see we actually compute the cost functional 3 times for each material. And every time it gives us an interface. So for example, for this material, we have this interface and then this interface that gives us the 2 points. That is it. So here you have the interface for material.
Yes. If you are more, that is if you are in this case, in the filament problem.
Okay. Okay, so this is our turn. So Antoine, Alexis, and I will present you our project of the CEMRACS 2018, which was the optimal release of mosquitoes to control dengue transmission. And our supervisor were Luis Almeida, Yannick Privat, Martin Strugarec, Nicolas Vauchelet, et Jorge Soubeli. So, the main articulation of our presentation will be a little introduction and then the optimization problem. So in third part we will see the numerical result, then the Gaussian release, and we'll finish with later perspective. So dengue is one of the most dangerous diseases for human health in the world, and according to the World Health Organization, 390 million of persons are infected by dengue per year, and 3.9 billion of people are at risk of infection with dengue viruses. And so this represents approximately 40% of the global population. So despite a lot of research on it, there exists no vaccine against dengue, and so we have to find a way to control the vector population. So the vector population of this disease is mosquitoes of genus Aedes. And we say that it's a vector because the disease needs its mosquito to be transmitted from one human to the other. So it's easy. Just if one human have dengue, a mosquito bit him, and if he go to bit another human that was not infected, he become infected. So in France, we have one Aedes, which is Aedes albopictus, that can transmit dengue. And so this is the tiger mosquito, the white and black one that you can miss here in Marseille. And so he appeared in France here in 2005. And so he started to migrate across the France, but just in 2010, and today in 2018. So this is the map of its presence. So in red, it is present and it can reproduce. In orange, please don't. In orange, it is present, but we do not find eggs. And in white, no presents have been recorded. So how to control this Aedes population? So up to now, we use pesticides, but now we are all agreed to say that pesticide is not a good deal, because, well, Aedes mosquitoes can develop a resistance, and pesticides are not useless. And also because if mosquitoes can develop a resistance, this is not the case of a lot of other insects. And the past decades, we lost a lot of insect biodiversity. And so now we are developing new methods. So, for example, you must heard that we can release non-fertile mosquitoes to replace the population in place. But today we will speak about the Wolbachia bacteria technique. And this technique seems to work because it was tested in Rio and Australia, and it works. So what is this technique? So it's Wolbachia. It's a bacteria that live in 60% of insects naturally. And but now in Aedes. And what scientists do is that they pick this bacteria in Drosophila melanogaster, so this is a fly, and put it into Aedes aegypti. And what they find is that these bacteria inhibit dengue transmission. So these bacteria are other effect on the mosquito population. So there is a vertical transmission of the bacteria. Is it to say that this means that if a mother has the bacteria, all her offsprings will have the bacteria? There is a cytoplasmic incompatibility, so there will be no viable eggs when uninfected females mate to infected males. And the bacteria reduce lifespan, so the death rate of infected population of mosquito will be greater than the death rate of uninfected mosquito population. So, knowing this, we develop our research questions, which is how to spatially release Wolbachia-infected mosquitoes population to have an invasion in a given time. So, practically, we can make, in lab, we can breed a lot of these mosquito because it's costly and it needs time. So, the practitioner go on field with his box full of mosquito, and he have to open it and release mosquitoes in the area that he want. So what we want to know is where do we have to open this box to have the more efficient development of our population of infected mosquito.
So here is the main equations. It's two coupled direction diffusion equation. So the function involved is N1, which represents the uninfected mosquitoes, and N2, the infected mosquitoes. There is two parabolic parts and a reaction term. For the reaction term, there is burst time for the logistic burst time, and a death term there and there. For the uninfected mosquitoes, the burst time is penalized by the infected mosquitoes, the proportion of infected mosquitoes, because of the vertical transmission. More you have infected mosquitoes, more the offspring will be infected. And so it's obvious. Also there you can see the control. This is the number of infected mosquitoes that were released in time and in space. For the boundary condition, we put Neumann condition, which means that the mosquitoes cannot go out of the domain and there is no mosquito which go in the domain. Okay. Also, I forget that the burst time, in front of the burst time, there is 1/epsilon, which means that mosquitoes produce a lot of eggs, and this is why there is 1/epsilon. And when we combine the two previous equations, and we focus on the proportion of infected mosquitoes, this is what we want to study, and when we let epsilon goes to 0, we find this equation. So this is again a reaction diffusion equation with a parabolic part, Fp plus the control, U times Gp. Okay? There is still a Neumann boundary condition. And first, we'll focus on this equation. So dTp minus Laplacian of p equals Fp, with F, which is a biostable reaction term. So this means that there is two stable steady states, 0, which are constants, 0 and 1. Theta is also a steady state, but it is unstable. And there is many properties of such reaction term. For instance, if the initial condition is constant and less than theta, so you go to extinction. That means that when t goes to infinity, p of t goes to 0. And this is the reverse. When the initial condition is constant and greater than theta, so you have inversion. So when t goes to the infinity, p of t tends to 1. So you see, you can reach inversion or extinction. But this is not the only way to reach inversion. For instance, thanks to the comparison principle, which means that if at the initial data we can compare the initial data, the solution will still preserve the order. And so if the initial data is greater than a well-chosen indicator function, the solution will invade. This is also the case for bubble function. Bubble function are a function like that in 1D. this is just the shape. Okay. So we have with dTp minus Laplacian of p equal fp, and now we focus on the control. The biological assumption on the control are the following. The laboratory cannot provide as many mosquitoes, so we have to bound the integral over 0t and over omega of the quantity of mosquitoes which are released. And also we can release as mosquito as we want in one point. So this is the second condition. Okay. We also made a strong assumption, which is the following. The time scale is about 100 days, and so we think that we made the assumption that the release are instantaneous. So we modelize it by this fact. So there is 1 over delta, and the release, there is a function over space, and the indicatrice over a small time lapse. And when we let delta go to 0, we find this equation. So there is the equation that we already have saw, dTp minus Laplacian of p equal fp. And here is the control. So there is jump at given time. The jump depends on the quantity of mosquitoes that we release and on the quantity of mosquitoes infected, the proportion of mosquitoes infected, which are already there. Okay? And so now we have fixed the control. We want to catch the invasion. The invasion, so we want to, the code function is the following. It's GU, which is the integral of 1 minus p the whole squared. And so when p is almost 1, g is almost 0, and so there is invasion. Okay. Fortunately, there exists a solution, a minimizer of g, in the set of functions that we consider, but we do not have any result about uniqueness. And for symmetry reason, I think that it's not true. And so, to sum up what I've said, the goal is to minimize this functional, where p is solution of this function. Okay, here we only treat one release. Numerically, this is what we have done because we have some problems, so we want to go further, but we don't have time to go further. Antoine will present it. And here is the constraint on you. So now I'm letting Antoine present you.
Okay, thank you. So yeah, I'm going to start. I'm going to talk about how we tried to solve this numerically. So yeah, we're just looking at a single release. Okay, so it's with the initial condition that we're controlling. And so this is an infinite dimensional optimization problem. So if we want to solve it numerically, we're going to have to first start off with the discretization. And so for this, we actually chose to work with finite elements. The main reason was actually because we wanted to work with FreeFem++, which is a program that does finite elements. And the nice thing about it is that it has an interface with IPOpt, which is a program for solving, very large, very complicated optimization problems. Okay. So to remind you, when we work with finite elements, we have a basis of a finite basis of functions, and so we can expand the functions in our problem as a sum of these functions. And so essentially, what we're trying to find now is these coefficients, these UI, and these describe our control. Okay. And so then we have a discretized version of every component of our optimization problem. So to start off with, we have the cost. It's going to depend on the coefficients for the control. And so we have to compute, so first off, the associated solution of the PDE, and then the integral, and all this is pretty straightforward with FreeFem. Then the constraints, so again, it's really just straightforward. We have just the control that has to be bounded, and again, we can compute the integral very easily with FreeFM. The next thing that we have to do for IPOpt is that we have to give them the gradients. So first of the gradients of the costs and the gradients of the constraints. Of only the non-linear constraints. The rest he understands it easily. So for the gradient, what we did is we used a theoretical result. We actually started by looking at the gradients in the continuous case. And so you can compute these. So if you consider a control and you consider an admissible perturbation, then you can compute the Gatto differential. So here's the expression, right? It's an integral of your perturbation. And it depends on Q, which is the joint, in the sense of our PD. And so to get the discretized version of this, what you do is, again, you expand your perturbation in your basis of functions. And quite simply, what you get is that the kind of partial derivative corresponding to the coefficient I is going to be this integral with the test function I. Okay? So again, to compute this in FreeFrame, we have a control. We first have to solve the PD with the P, we get the final time solution, and then we have to solve a second PD backwards to get the Q corresponding to time t0. Okay, and so you have the same thing for the function of the constraints, but it's really just a lot simpler because it's a linear function, so it just ends up being the integral of the phi. So it's just like this term. Okay. So with all that, we could program it in IPOpt, and so to start off and to kind of get to learn IPOpt a bit, we started actually with a simplified problem. So we forgot the nonlinear term, the reaction term. So we end up with just the heat equation, and we're controlling it with the initial condition. Okay, and again, same kind of constraints. And this problem is actually sufficiently simple that you can solve it theoretically. And it's actually simple enough that you can show that the control, is the optimal control is just a constant. And it depends on how your constraints are, but basically you're saturating the constraints. You're doing really, basically releasing the maximum amount that you can, okay? So we had this result, and then so we coded everything in FreeFrame, and we got it to run. Had a few problems, but essentially it was working, and we were happy with how it was going, and we were solving it. Okay, and so then we moved on to the real problem, and so we knew also that we had similar results like these. Well, not as theoretical results, but we had intuitions on what the solution could be. In particular, and so it's going to depend on how your constraints are, right? But so if you remember, there's a certain level for the theta, which is the level above which your reaction term, so if you come back to the equation here, with the F is going to be positive if you're above theta. So you know that if you have your constraints that are such that you can have an initial condition that's everywhere above this theta, then your solution is going to invade, it's going to increase and stuff. So this is one of the first things that we actually wanted to find. And in this case, so it corresponds to when you have your constraint on the integral of the control, which is greater than g of theta. G is just the function that allows you to go from the density of mosquitoes to the proportion of mosquitoes in this case. Okay, and so we were somewhat able to find this solution. So here we've got this is the initial condition, okay, and you see that it just behaves like a constant solution. It just rises up. There's a couple of things that you can note. It's essentially that it's a bit higher on the boundary. And so the way we understand that is due to the boundary conditions, actually. We considered Neumann boundary conditions, so the mosquitoes can't leave. And so in particular, the way you can see it is that, well, the diffusion is less, it has less of an impact, it has less of this spreading impact on the boundaries, so there's an interest in putting more on the boundaries. Okay, but this is not very interesting in practice because, well, what it means, so if this is the density of mosquitoes that you need to release, you'll notice that it's everywhere positive, and it's constant. So it means that the guy with his little box, he has to go and run around everywhere and just release a few mosquitoes all over the place. So it's not possible in practice. The second thing is that we notice that actually when we run IPOpt, it depends a lot on the initial guess that we have to give it. We have to give it like an initial idea, and it starts off from that. So what we did is we gave him instead an indicator function. So just you know, a certain level in the middle. And so it ends up finding something similar to an indicator function, except that again it increases it on the boundaries, okay? But then the behavior on this one is actually fairly different, because you can see that first off it increases in the middle where there's the release, and then you have this sort of traveling wave that then goes and invades the whole of the domain, okay? And so this is again a bit more interesting as a result, but again, it's you might not see it very well here, but again, it's still positive everywhere. So again, you still need to release a few mosquitoes everywhere. At this point, maybe so this is again, it's still in the case where you could have a constant solution, right? But it's telling us that this actually is a bit better. So one thing also to mention is maybe in terms of parameters, one of the parameters that's going to have a very important, that's going to have a lot of importance is actually going to be diffusion. And so if you take a diffusion parameter that's a lot bigger, so I think like before it was 2 squared meters per day, and this is 12 square meters per day. What you get is actually this behavior, this would in optimal control you call this bang bang behavior. It's actually a lot more present, and so you can see that actually with the diffusion is very strong. So it just disappears eventually, and it actually kind of behaves more or less like a constant solution, really. But it does tell you that if you have a very high diffusion, you can kind of release everything in one spot, and then they spread out, and then they all increase. Okay. So this is when we were successful, but then we started looking and considering, okay, but you know, it's very costly to develop and to breed these mosquitoes. So what happens if we consider, you know, a very low amount of total mosquitoes that you can produce? And essentially, we never were able to get the program to work satisfactorily. We were somewhat able to get it to give us an answer. So this is the case. Now, what we did is we basically told IPOpt to stop as soon as it had a very high tolerance. So as soon as it kind of looked like a solution, we told it to stop. And the frustrating thing is that the solution that we get is kind of interesting because it looks really like 2 releases on the side. So it's like 2 releases that have been on the side, they grow, and then you have traveling waves that invade the whole domain, okay? Now, why it doesn't work, we're still trying to figuring it out. I think we know pretty well the error messages of IPOpt by now. But essentially, I don't have a definitive answer to give you. And so yeah, as a summary, in this case, yeah, it's whenever we consider a small total amount of mosquitoes. The other problems with this is also that just how dependent on the optimization parameters IPOpt is. So you have to get it to work. In the first case, we had to play around with the scaling of the variables, and if you choose 2 different scaling parameters, you end up with 2 different solutions. And so really the other major problem is that, well, these solutions are not really feasible in practice because you have to release mosquitoes pretty much everywhere. So to deal with this, what we thought about another problem, and so it's to restrict even more the kinds of controls that we were going to do, and so we considered controls where we're only releasing in several points. So here it's going to be we're going to have k releases in space, and each release is going to be a Gaussian distribution, right? So just in a single point, okay? And so we did it, and we chose it so that the total amount of mosquitoes again is still C. And so in this case, what we're trying to do is we're trying to choose these XKs, which are going to be the centers of the releases, okay? And in which is like the best positions for these K releases, for them to have an invasion, okay? So we were able to get this to work, but again, we find some difficulties, mainly that, well, depending on the initial guess that you give it, it gives you a completely different, well, somewhat different solution. So up here, these are all the initial guesses that we give it. So sometimes we, a straight line, a weird diagonal, or just randomly. And so you see that actually, first off, it doesn't move a lot. You actually kind of stay in some cases, sometimes it doesn't. But still we were able to more or less to get it work. But again, this is actually really in a case when I don't have it here. Okay. But when the time interval is really big. So another problem that we had there is if you don't have full total invasion, IPOP just doesn't seem to work, right? It can't give you a solution when the final proportion of mosquitoes is 0.75 or something like that. And again, we had some problems. So if the amount of mosquitoes is really small, it wasn't working again. Okay, but still we had some cases, and so I'll pass it on to Claire so that she can finish it off.
Okay, so after we wanted to know if we can divide our C, so our amount of mosquito on the depot, to 3 or 4 or 5 or 6, does it will okay, so hit invade because with IPOP, so it works. And what we wanted to know is where do we have to launch these boxes, and what we say, so with 3 is just before Antoine says us, and after 4 and 5 there is not a big shape that, we didn't know the shapes are just, I don't know how to say, well, from 6 we can see a diagonal, and one of the most perspective of our works is to have a large number of releases of this Gaussian in space to see what happens if we have a large number of boxes, and what would be the shape of release that we have to do for being the more efficient. So a second perspective will be to take into account the cytoplasmic incompatibility, because here we take into account that all the offsprings issued of an infected female and a non-infected male will die, and this is not really the case. That there is a little proportion of eggs that can hatch, and we know that we have to take it into our numerical result, but we already code this, so this is just to search.
Yeah. So just to finish off, maybe a bit more in the technical aspects of the thing. I guess the most important would be maybe the changing the boundary condition, because we saw just how much it influences the solution, and it's not really even realistic, but it's simple to implement. So then, if we wanted to actually, in terms of solving the problem, I think maybe if we change the cost function and then eventually the whole optimization problem. I think it's one idea that I have of why it doesn't work is because there just isn't enough of a trade-off. You have too many solutions that can invade, and you have too many solutions that invade at the same kind of level, and so you have some kind of flat regions in the cost function, and so eventually it kind of gets stuck somewhere in some problem like that. There's another way you can implement the optimization problem, actually. So we hid, in a sense, the PDE in the cost function, but actually you can consider it as a constraint. So you have to add the variable p, and at every time step as an optimization variable, give that to IPOpt. And so the cost function becomes very simple, it's just the integral of the last one. But then you have a very complicated constraint, which is so your numerical scheme, right? And that you have to write, and you have to write that as, and each time step, each equation for each time step becomes a constraint. So it's a lot more work, but actually we realized, I was reading these things about IPOP last week, and I realized that actually it's more like that you're supposed to do it, or that people do it. So maybe that was one of the reasons. And yeah, finally, it would be nice to know why IPOP doesn't work in our case. But yeah, thank you for your attention. Yeah, absolutely. Yeah, we noticed it, and so again, yeah, maybe I might have said it very briefly, but we were really only able to get it to work when it's very long, and well, not so much actually. It's sometimes I don't know, it's very mysterious on that one, on that case, but we didn't. I didn't notice anything special on that, other than yeah, it seems easier to solve when it's larger. When it's large, when t is large. So the solutions that IPOpt gave is are not a good solution because they invade, but any invasive solution would invade. So why consider one instead of another? We have too much time, and this is one we need to either increase the size of the domain, either decrease the time. This is the same. Yeah, this is fine. And this is two generation of mosquitoes, but I think that the domain is too small. It's only 1 hectare, and yes, I don't know English. 1 hectare. Yeah, for the case, maybe different.
I have one. I don't understand if you try to minimize the number of mosquitoes that you release.
Yeah, so that would be one of the solutions, or one of the ways to kind of get a different optimization problem. But here, yeah, we're just asking what is the initial release that allows us to get to the closest to invasion, or that has the minimum cost. But we don't have any penalization of the mosquitoes. And actually, I think there was you can actually show that the constraint here, where you say that it's the integral, so the total amount of mosquitoes has to be less or equal than C. It actually in practice turns out to be saturated. So it's actually, we could have put equals to C in the end. And there's no point in not releasing mosquitoes. It's fairly intuitive.
biological modeling and cell migration, with coordination with Christelle, Nicolas, and Laura. Okay, we may start our talk with a short biological introduction, and then we will introduce different stochastic model to study the effect of the environment on the cell migration phenomena. So, cell migration plays an important role in a wide variety of biological experiments. For example, in immune response, leukocytes migrates to the areas of insult to mediate phagocytic, and in metastasis stage of cancer, tumor cells. So tumor cells. It's not working. Okay, anyway. So tumor cells migrate from the primary tumor, circulates throughout blood vessels, and then migrates again toward a new site. So the cell is an active system in a sense that it can take energy from the environment and convert it into directed motion. In this project, we are interested in the question of the influence of the environment on cell migration. So how can the environment affect the cell migration? In particular, the effect of chemoattractants or presence of obstacles in the environment. How can this affect the behavior of cells? Okay, in the first video, we see that the cell has a Brownian motion, while in the second video, we can say that the cell has a ballistic motion. So we have a different type of trajectories, and from biological point of view, cell crawling phenomena over a substrate can be divided into 4 steps. At first, the cell extends a protrusion in its direction of motion by achatin polymerization. Cell protrusion are divided into 2 types. The first one is the lamellipodia, which are wide and flat, and the second type is flipodia, which is finger-like extensions. Maybe it doesn't work. Okay, so the first step, as I said before, that the cell is producing a protrusion at its leading edge, and then it adheres in the frontal side with the substrate, and then it adheres at the cell body substrate rear. And finally, the cell moves due to... Okay, this is... Okay, thank you. Okay. And finally, the cell moves the whole body due to the forces at the cell body, body and the cell substrate rear. Now we introduce some models to describe cell crawling on substrate. We present a 2D discrete model introduced by Christelle in her PhD thesis, where cell is considered as a point with arms. The arms are the flipodia. And protrusions exerts forces exerted by flipodia, and these forces are normalized. So in polar coordinates, the forces are characterized by the angle theta I. And from force equilibrium law with no inertia, we get that the sum of all protrusions forces here equals to minus the friction forces. And we remark that the cell tends to produce protrusions in its direction of motion. Okay, in this project we are interested in the 2D the 2D continuous model which describes the cell velocity from protrusion forces. This model is studied by Christelle, also in her PhD thesis. In fact, the velocity of the cell is given by the following formula. C is the rate of reproduction of a protrusion in the direction of the velocity of the cell. Gamma is the friction parameter when the cell crawls, so it exerts a friction on the substrate. And alpha is the sensitivity of the cell to produce protrusions in the direction of the cell velocity. And lambda is a parameter related to the lifetime of the traction forces. At the end, W is a 2D Brownian motion, and sigma over gamma is the noise intensity. First, we consider the 1D model without signal, without the effect of the environment. The 1D stochastic differential equation reads as follows, where V now here is a random variable in R. And if we denote by P is a probability distribution, then we get that P satisfies a Fokker-Planck equation. At stationary state, we have delta P is 0. So we get, at the stationary distribution state, P satisfies the following formula with N is a normalization parameter, and the potential W can be calculated explicitly, and it equals to the following quantity. We can notice that the most probable velocity V corresponds to a minimum of the potential W. So we are interested to find the minima of the potential W, and we study the number of minima of the potential W according to the sensitivity parameter of the cell to produce protrusions in the direction of the velocity. So in the case when alpha between 0 and 1, and taking these parameters into account, the potential W has a unique minimum at 0, which means that the most probable velocity is 0 of the cell. And we will see later that this corresponds to a Brownian motion. While where alpha is greater than 1, the potential W has two minimums at V1 and V2, with V1 equals to minus V2. And the value of the potential W is the same at both V1 and V2, so that we have two different velocities with the same probability. And we will see also later that here the cell will have a brilliant motion. Okay, for the numerical stimulations, okay, we take an interval of time 0t with t equals to 1000, and we take the time discriminant 10 power minus 2, and we approximate the position of the cell at time step tj by the following formula. And the velocity v is calculated by the 1D SDE. And we use the Euler-Maroyam method to approximate the velocity. The difference Wj minus Wj minus 1 is an increment to d motion, which is like a normal distribution of variance dt. So numerical simulations shows that when alpha is less than 1, for example, alpha equals to 0.1, the most probable velocity is, or the most frequent velocity is 0. And the trajectory described by the cell is really a Brownian motion. Okay, I have escaped in the first of the, okay, no. this video. So this describes this cell type trajectory. For alpha is greater than 1, normally we do the numerical simulations for alpha equals to 10. We have two velocities which have the same frequency, and one is negative and the other is positive. And we see that the trajectory described by the cell is brilliant, which is shown by the second video at the first. So we can conclude that this simple 1SDE, stochastic differential equation model, was able to explain different types of cells' behavior. Maybe now it's time to explain the effect of the environment, such as the signal, on the cell behavior. Maybe you can explain it.
Thank you. So now, as we saw in the biological introduction, the environment can influence the cell migration, either mechanically, which means that, for example, with obstacle or different type of substrates, or either chemically. With chemically, we mean that there could be some chemoattractants, so some agents that can attract or that can influence the motion of the cell in order to let them towards them. So in this case, till here we want to present a model that takes into account an attracting signal. We present here the stochastic equation for the velocity. This equation is well studied in the article of Christelle and Nicolas, Growling migration under chemical signalating. And here the attracting signal is represented by the parameters beta, that actually is the sensitivity of the cell to create a protrusion in the direction of the signal. So now we are going to analyze this differential, this stochastic differential equation by analyzing both the parameters alpha and beta. So we start by the one-dimensional case. In the one-dimensional case, the signal does not have an angle, but it has a direction. And these components, we can see this part in this scene plus minus in the equation in front of the terms relating to the signal. So as before, we can, if we define by PS the distribution density of the velocity, we can show that this PS solves a Fokker-Planck partial differential equation, where actually the signal term appears in this function in F plus minus. We can also, as before, obtain the stationary distribution, where we obtain also this formula that is the new potential that takes into account the signal term that is linear with respect to V. So now our aim is to study the minima of this function with respect now, not only with respect to alpha, but also with respect to alpha and beta. So the minima points are going to change. So now we can consider, for example, a W minus. That means that we are considering a signal in the negative axis, so here. And we consider these parameters. So here we plot the graph of the W. So here for alpha between 0 and 1, we see that we have only one minimum point. It's not so clear here, but actually here the minimum point is strictly negative, while before it was 0. Here it's strictly negative. This is before we have a signal. And here for alpha greater than 1, we have a sort of double well potential. But here, actually, the minimum in the negative side is greater. The values of the minimum in the negative side is greater than in the positive side. This is also because we have a signal. So now we compute the numerical simulation with alpha is equal to 0.1 with the same scheme of before. So actually we see, okay. So actually we compute the discretized density probability. So we see also that it's centered in negative value. And here we see clearly that the cell is able to follow the signal. So the cell is starting from 0. The signal is in the negative part. So we see that it's going to decrease. But we see also that we have a lot of noise, actually. So this is due to the fact that beta is still little and also alpha. So the noise term in the stochastic equation is still significant. If we change alpha, so if we take alpha is equal to 10, so we obtain a sort of a double well potential where actually the negative velocity is the most probable one. And here we see that the cell is able to follow the signal a long time, but actually there is some times in which the cell is going in the wrong direction. So along the positive part, here for example, or here also. And this is because alpha is equal to 10, so it's like the cell is polarizing, so it's sometimes she is going to not follow the signal. So the conclusion is that for a weak signal, the cell can follow the signal, but there are significant interval of time in which it can go in the wrong direction. Now, if we take always a negative signal, but with a strong signal, so beta is equal to 1, here what we see is exactly as before. So the minimum for alpha less than 1, the minimum is only one minimum in the negative side. Okay, and here what it happens is really interesting, because for alpha is greater than 1, we do not have a sort of double well potential. So it means that the signal is strong enough to kill the velocity, the positive velocity that could appear here, and to enforce the negative velocity in the negative side. So here the signal is very strong to dominate. We compute so numerical simulation. So here, as before, we see that the histogram is centered in the negative side. And here we see that there is a more direct motion toward the signal. So here the noise is really lighter than the before, with beta is equal to 0.1. So we tried the same simulation changing alpha is equal to 10. So actually, yes, we can see here that there are some probability of having velocity 0 or velocity positive, but still the most probable one is in the negative side, and also here we can see a direct motion towards the direction of the signal. So in conclusion, if the signal is strong, the cell will always follow the signal for any alpha. So also in the case for which the cell is polarized. So now an interesting case to analyze is even if we have a strong signal, so even if we have a beta is equal to 1, can we find a set of parameters for which the cell could escape from the signal, so could go in the wrong direction? So what we need actually, we need to aim 2 ingredients. So the potential must have 2 minima, and these 2 minima and the values of these 2 minima must be the same. So mathematically, it means that the potential W must be an even function. But actually, what we obtain from the expression of W, the signal gives to W a property to be not even. So the best that we can have is a global minimum in which we have V1 that is negative, and a local minimum that is V2 that is strong, that is positive. Okay. So now, speaking in calculus, so we set beta is equal to 1. We consider a negative potential, a negative signal. This is the potential. So we can see that here, this gives the non-even property of the function. So if you want to find the minimum of the function, actually we want to solve. We derive this function with respect to v, and we want to. And it's equivalent to solve this equation. So this equation means that we are searching for the intersection point between this function, so the hyperbolic tangent of alpha v, and this function, these lines. This is an integer that is positive since beta is positive. So what we can do actually is to try, the aim is to take great values of alpha in order to increase the shape of the hyperbolic tangent around 0, and increase this quantity, that is the slope of the line, in order to let this function touch the hyperbolic tangents, in order to have this true positive intersection. So our aim is to find, so our set of parameters is great values of alpha, and this ratio less than 1. So actually, even if this analysis seems to be easy to compute for find these two intersections, when we find the solution of this equation, in the positive axis, and we put this in the values of W, still the W have a great difference. So in the negative side is bigger than in the positive side. So for example, if we take lambda is equal 1, tau 2, and alpha 100, this equation has 3 solutions, so V1 less than 0, and 2 solutions, V0 and V2 strictly positive. But here, as I told you before, so we are able to see one minimum, and another minimum here, but we see it's clear that this value is really stronger than this one. So, and actually this happened for any type of parameter. So we conclude that for this kind of model, we are not able to find a way to control the cell in order to escape from the signal if the signal is strong. So we think about another type of tool that is a time periodic signal. A time periodic signal, it means that we define the period of the signal, so n times dt, and we have a switch system of the stochastic velocity. So for the first n times dt time, we have a negative signal, and then we change with a positive signal. So how we can adapt this idea to the previous case? So actually, the idea is the following. So we have our interval of time, 0t, okay? So we start by initial velocity that is positive, that corresponds to the minimum in the positive side. We run the simulation with a negative signal, so in this direction. So the velocity is going to decrease. This is the graph of the velocity. This is positive and negative side. It's going to decrease. Then when the signal is going, when the velocity is going to arrive here, so we keep exactly the last time for which the velocity is positive. So we have, for example, j. And starting from here, we define n. So n as before, n is equal to j. And so from here to here, we start by our time periodic signal. So in this sense, we have for the other j, we have a positive signal, and for 3 times j, we have a negative signal, and so on. And what you can see here is that we can have, this is the velocity, and this is the trajectory. So we can see that there is a significant interval of time in which the velocity is, so the cell is going in the wrong part of the signal. So with this method, we are going to a little bit control the cell with respect to the signal. Okay, now we can speak about the effect of obstacles on the cell migration.
Thank you, Alessandro. So now we are interested to study the effect of obstacles and the behavior of the cell in presence of signal. For this aim, we suppose that we have a single moving cell on an environment containing a uniform distribution of obstacles, and we suppose that the cell can be attracted by a signal here. And for modeling this experiment, we use 2D stochastic differential equations so that we can compute the velocities. And since to avoid overlapping, we use Ozawa algorithm. Hence, primary simulations shows that. Okay, at first we will see that the cell is following the target here. And after, the obstacles like the wall and here the uniform obstacles are trying to modifying the cell motion and preventing the cell from going and to the target. Okay, so this is really primary simulations, but we can see that the obstacles are trying to prevent the cell from going to the signal.
Wait. I cannot use Mac. Sorry. There is only the slide for the conclusion. Okay, this one. Okay, perfect. Thank you. So for the conclusion, in this presentation, we present three stochastic differential equations. The first one without signal, and it's an important model because it's simple and it's able to describe different type of cell. The second one is the model in which we take into account the signal, so in which we see that the cell is going to follow the signal. And the third one is a model with a periodic signal in which we have found a way to control the cell. And then we try to implement to do a third implementation of the contact cell, so the contact algorithm, and so to see. So for these 4 points, we can see how the cell behaves without signal, with signal, and with the presence of signal and obstacles. So future works could be, for example, a theoretical analysis for the persistent time with respect to the parameter regarding, for example, the stochastic equation. This means that maybe it's interesting to study analytically the time for which the velocity will be positive in the sense of the signal, so that we can act better maybe to control the cell. Another part is to make a numerical study for the effect of the obstacle in this algorithm, so maybe to create a pattern of the obstacle in order to trap the cell even if there is a signal, so to see how the cell will behave in the trap. Also, an important part is to introduce the cell internal dynamics in all this model. And the last most important object is to use all these results in order to create model for collective cell migration, so considering a lot of cell. So thank you for your attention, and any question is welcome. Yes, exactly. Yes, you can compute analytically. Yes, but we didn't try. But yes, without signal, it's proven the time persistence. For example, the time if we start from a positive velocity, the time in which the velocity will go in zero, so we will pass through zero. Yes, it's possible. Yes, yes. The open work actually is in the signal part. So do a analysis persistent time in the signal part. Yes, that is more difficult, I think. Thank you.